Hi guys, welcome, and today in this tutorial we will take a look at how to configure our ADC module so that it can work in a non-blocking way. Previously in the previous tutorial we saw how we can configure the ADC, and we have seen all the basics, and today in this tutorial we are going to take one step further. In this tutorial we will see how we can use the ADC module with the interrupt. In the event we are just going to calculate the value. So today we are going to work on a single shot mode. So in a single shot, once we call the function, it just takes a value as a sample, and the samples could be many. It depends on the buffer we are going to create. So we will see how we can create the buffer and create those samples. In the single shot mode we just simply give a request for the samples, and we read the samples value for one time only, and we will see how we can use the ADC in a continuous mode as well in the later tutorial. Okay, so first of all let's start our project. So just go into computer and then C directory. Here we have nRF SDK, and go into the examples, and we are going to copy an example from the peripheral, and here we will copy this SAADC. SAADC is basically successive approximation analog to digital converter. So go into my projects and paste it here, and let's rename it as SAADC single shot non-blocking. So open this folder, go into PCA10040 if you are using nRF5 2832, go into the blank, into SES, and open the EM project file. And let's remove this. And I'm going to zoom in a little. So to zoom in, just press Ctrl and use the mouse scroll. Okay, we are ready to configure our ADC with the event, and first of all let's see how we can change the resolution of ADC. So I'm going to paste here some information, so it would be very helpful. So let's see. So as you can see, I have calculated some of the stuff for you guys, so you can easily see how much resolution do you need in your projects. For example, like if I don't need a very strong resolution, and I can easily go with the 8-bit mode, and if I'm using a normal resolution, then 10-bit is okay, and 12-bit and 14-bit is for special things. If you want to measure very small changes in the voltages, approximately this change is one value in 12-bit. Okay, so we have some of the values here, as you can see, and to configure the ADC's resolution, just go into the SDK config, right click here, and open the CMSIS configuration wizard, and you have to change the resolution from here. Go to the drivers, and here in the drivers look for SAADC here, and click on the resolution, and from here change it to 12 bits. And one more thing, go here, SAADC nRF legacy drivers, so you have to change the resolution here as well, otherwise it won't work. So change it to 12-bit, and click on the save button to save it, and then close it. So now our resolution is 12 bits. So today we will see how we can configure according to 12 bits. We have this resolution, and it's basically divided over 4096 values, quantization levels for 12-bit. Okay, so first of all let's create a buffer that I mentioned. So to create the buffer we need to define some specific value. So this depends on how much samples you want. Let's say let's go with the 5. This is going to be the number of samples that are going to be stored in the buffer, and we will use two-dimensional array to store the values in the buffer. So we have this variable that we previously used as SAADC value. Basically this variable stores 16 bits of values, so we use this variable to store once they are read from the SAADC module. So we have created a buffer pool, and let's say it's a two-dimensional, so it's going to be 2 buffers, and here we will just give the sample buffer length. Okay, so we have created a buffer with the 2 dimensions, and it has a length of 5. So the next thing we need is if you want to count the number of events, you can use an event counter as well, and if you don't want to count them, then just leave it. Okay, the next thing to do is we have to create a callback function and the initialization of SAADC module as well. So first of all, let's initialize. I name it as SAADC, and we will initialize it here, and of course we are going to need an event handler for that, so I'm just going to call it SAADC callback, and in this we are going to pass it the event value, so it's going to be this specific structure that's going to be passed, and we will use this pointer to later on retrieve the values from the structure. Okay, we have the callback handler. So basically this handler is going to be called every time an event is generated by the SAADC module, and once it takes the sample, it's going to generate this, and it's going to transfer the data via DMA, direct memory access module, to the memory in this buffer space, and we will take that data and do our calculation on that data. So let's initialize the ADC. This is going to be the error code. The next thing we need to do is we have to configure the channel, so I'm going to use this channel config t, and I'm just going to name it as channel config, and let's give it the values as default, so nRF5 config single-ended. Okay, so this time we will be using the single-ended. So this time I'm going to use channel number 5 because it's going to be connected on pin 29, and I'm going to use that because I'm going to use some external sensor, and today we will be taking a look at LDR, which is light dependent resistor, and its resistance changes according to the light around it. The more the light falls on the sensor, the resistance decreases, and the resistance increases once there is less light falling on the LDR, light dependent resistor. So we will be connecting that on pin 29. So I'm going to configure the channel 5 for that, input 5. So this is connected with pin 29. Okay, now we need to initialize the ADC, and first we need to pass it some configurations, and we don't need to pass any configurations, we will just pass it null, and we can easily configure using the CMSIS configuration wizard, and you can see you have already seen that I have configured the resolution, so I don't need to pass any configuration settings from here in the initialization of the ADC, because we can easily configure that through SDK config.h. So we are not going to pass any of them because it's automatically going to take those configurations and do the configurations for us, so we don't need to pass any configurations. And the next thing is we have to pass it the event handler, so I'm just going to put the event handler name here, and it's done. And now we have to check if there is an error. The next thing we need to do is we have to configure the channel, which channel we will be using. So I will be using the channel 0 again, because we can connect any channel but the pins are connected with the analog input are hardwired, so be careful when you connect the pins. But we can configure any channel, and we can allot any channel to these pins. I'm going to initialize 0, and I will pass it the channel configuration values. The next thing I need to do is I have to give the buffers. So we remember we have created a two-dimensional buffer. So basically we need a two-dimensional buffer, so the values will be transmitted to first buffer, and if there are new values that are occurring, the previous will be transmitted to the second buffer, and the new values will be overwritten on the first buffer. In this way we don't lose any values, and this is all handled by the DMA. So when these samples are being taken, the processor is free because the DMA is doing the memory transfers. And here I have to give it the buffer pool and allot it sample buffer length. And we have to allot the second buffer as well, because we are doing the double buffer. So if there are some additional values, they are overwritten on the first buffer, then we have the second buffer to move these values to. Okay, we are done with the configurations. Now we need to do the calculations. So first of all, let's create a variable float, and let's give it a name as well. Okay, so this is going to store our value, and now once we get the event, we will see if its pointer is equal to this value. Event done. Okay, so be sure you have this, and if the event is done, it means we can. So let's create a variable again for the errors. So whatever value we receive from the SAADC is basically in the 2's complement, and previously we used in the blocking mode we used a function sample and convert, which basically takes the sample in the 2's complement and converts them into a proper value, and they will be converted here using this function. And here we will point to the data, and we have to tell it the samples buffer length as well. So we are using this app error check, and in the logger, if we have enabled the logger, we can easily see if some error occurs. The log will print out these errors for us, so it's automatically connected, and it's working. It works automatically, so we can see all the stuff. Let's create a simple variable, and now it's time to print some stuff. We will initialize the log later. Let's just print the stuff from the log. So once an event occurs, let's just simply print that some event has occurred, and then we are going to take these values and we will perform some calculations on them to see how much voltage level we are getting. Like printf, we will use %d here. This is the variable which holds the value of each sample. So now we will calculate the values, so let's calculate them here. We have 3.3 volts, and due to gain it's 3.6, and we have changed our value to 12 bits, so it's going to be 4096 values. And once the calculation is done, we will print this value, so we will use nRF log. And here we will use a nRF marker, which is basically telling that we have to print a float value here at this position. Because we are using the marker, so we have to use the escape sequence ourselves. Otherwise this won't go to the new line automatically, so we have to place that here. Okay, so we have finished the event handling. So once the event is handled, it's going to do this stuff, and finally we have to initialize it, and let me show you a function which calls this event. So in the main function, first of all, let's initialize the log. And make sure you go to SDK config and open the CMSIS configuration wizard, and here in the log, if you go in the logger and disable the deferred, otherwise you are not going to see the stuff, because I'm not using the sleep instructions right now. Okay, click on the save, close this, and now we will just simply call the SAADC function, which is initializing everything, and then we will print a message for, let's say, application started. And now the last thing here we need to do is we have to call the sampling function. You can use some timers and some stuff. In the future we will see how we can use the timers. Whenever you will call this function, it's just going to take the samples only once, so it's called a single shot, and we have to call this function, so nRF5, and it's non-blocking. Once you call this function, the processor is free, and the ADC module works in the backend, and the processor is free to do anything. That's why this function is called non-blocking function. And now we will just use some delay. So I'm just basically taking one sample after every 1000 milliseconds, or after every 1 second. Code seems fine, so let's build it. Go on to the build, click on the build, and yeah, it's done, so it's built. So let's see how it works. Okay, so before we put our code in to the device, let me show you this LDR. This is a light dependent resistor module, and basically it's connected with a comparator and with some variable resistor, so we can change the resistance, and it's going to give a single output. So we have two pins here, one is D0 and one is A0. A0 is for analog and D is for digital. So if we just want to see some light, then we can just simply connect the D pin for receiving a single logic 1 or logic 0. But if we want to see how much light is falling on this light dependent resistor, we will use the analog pin. So I'm just going to make these connections. So I will be connecting it with 3.3 volts, so be careful with that. Don't connect it with 5 volts, just connect it with 3 volts. So I have connected my device, and here you can see if I put my finger on this, is the light is being turned off, because the receiver is now the LDR is not receiving any light. And if I move my hand a little back, the light falls on it, and this LDR is just giving some value. So this value is going to be read in analog form, and I have connected it to pin 29. So let's see what the value what is the value we are reading right now. Make sure your device is connected, and this serial port is also connected. Click on the connect, go to erase all, and download it. And now we have to see which port is connected. Right now with my PC it's connected with the COM6, so I'm just going to open the PuTTY and click on the serial terminal, click here, and put the COM6, and to go into device manager, just go into the PC and right click on this PC, and here just go into the properties, and from here you can go in the device manager and you can see which port is connected. So right now, as you can see, my USB is connected on COM6, which is basically the serial to USB converter. Okay, so the baud rate is 115200, so I will just open this on the COM6, and once I open it, and here you can see it's reading 5 samples. After every 1 second it's going to call the ADC, and this event occurs after every second, and it's the event, once the event finishes, it receives these samples and then it prints these samples out. So here we can see we are reading this voltage value and this output value for this, and if I move its face towards the light, you can see the value has changed. As you can see, the values are decreasing down, and if I move it away from the light, the values are increasing, and we can see the voltage reading as well. So by this method we can appropriately see how much the light is falling on the LDR, and we can use it for many purposes, and we can use it in many sensors. We can use this with many sensors. Hope so you have learned something new today, and in the next tutorial we will see how we can use the continuous mode using the PPI and timers, and this code will be available in the description link of this video, and also I will put some functions with some descriptions. Be sure to download it and play with this code. And if you like my video, please hit the like button, and if you're new on my channel, please subscribe to my channel and click on the bell icon to get the notifications on time. Thank you very much for watching. See you in the next video.